Okay, guys, we're on to Unit 3. We're going to talk about something called systems of equations. Before we really get into them, though, we kind of need to do some work on solution sets, particularly ones with two variables, and we're going to deal with equations in this first section. Remember from 8th grade, hopefully you saw this equation, ax plus by equals c. It's the standard form of a linear equation. This relationship can be represented as a line. Okay, so last year you worked with graphing lines. A lot of times you probably worked on them in y equals mx plus b form, but there's an alternative equation with that, and it's ax plus by equals c. Equations with one variable, like we worked with in the last unit, usually meant one solution. Sometimes they were all real numbers, sometimes they were no solutions, but generally when you solved an equation with one variable, you ended up with one solution. For example, maybe you had x plus 4 equals 12, and we know we would subtract 4 on both sides, get x equals 8. So one solution, one variable. In this unit, we're going to be working with two variables. Two variables usually mean more than one solution. More than one solution. So something like that would be in this form, and maybe it says 2x plus 3y equals 8. And you're going to see here shortly how you could come up with more than one solution. Let me cover some of this up here. Okay, example 1. Circle all the ordered pairs. Remember, we know ordered pairs are always x, then y, that are solutions to the equation 5x minus y equals 3. So there's that equation. And we are trying to find ordered pairs that are solutions. Now we just said when you're working with more than one variable, you could have more than one solution. So this isn't multiple choice where only one answer is going to be correct. It's possible that you would come up with more than one correct answer. Okay, and then part B, how did you decide whether or not an ordered pair was a solution to the equation? And yes, I want you to write out an answer. Go ahead and pause the video and do that. Parts A and B. Okay, here's my answers. What I did is I plugged in x and y into the equation, and I looked to see if I got a true statement at the end. So for example, in the first one, excuse me, I plugged in 1 for my x and 2 for my y, so I had 5 times 1 minus 2. Well, that's 5 minus 2, which is 3, and 3 does equal 3. That's a true statement, so that must be a solution. When I plugged in 0, 0, 5 times 0, 0, minus 0, well, I just get 0. 0 is not equal to 3. That is not true, so therefore that's not a solution. Negative 1, negative 8 did work when I plugged it in. I got an answer of 3. 2, 1 did not work. Got an answer of 9. 9 is not equal to 3. And 3, 12 worked as well. So finding solutions is as simple as just plugging the numbers in and checking to see if they give you a true statement. Part C, so keep going with this. Find more ordered pairs that are solutions to the above equation. Go ahead and pause it and see if any of these ones work. Okay, check your answers. I have that these two work right here. Do be careful with these signs when you have a negative number for y. For example, on 0, negative 3, I plugged in 0 for x, 5 times 0, and then I had minus from my equation, and then a negative from here, so minus the negative 3 should actually become a plus sign. So I get 0 plus 3, which is 3, and of course that works. I skipped D on here on this numbering, so don't look for it, it's not there. So from C we go to E. Create a table of values of all the solutions you have identified. Well, a table of values can simply be represented by a t-chart, x, y. We always put x in our first column, then y. So we have, what do we have? We have that 1, 2 worked. So 1, 2. We also have -1, -8. We have 312. Whoops. 2, 7, and 0, -3. Okay, so those are the 5 solutions that we have already decided will work for this equation. How many ordered pairs, we know ordered pairs are x, y, will be in the solution set of that equation? So same equation we've been working with. We've already identified 1, 2, 3, 4, 5 ordered pairs. Okay, so is our answer 5? No, we could find more. These would not be the only points. These just happen to be the only ones out of these 10 options that worked. But how many ordered pairs would there actually be? There'd be an infinite amount. Okay, we could find an infinite amount of ordered pairs that would work in this equation. Finally, create a visual representation of your solutions by plotting each point in the coordinate plane. Some of your points may not fit on the grid. Okay, let's check and see. So our first ordered pair would be, remember that this is really just 1, 2 as an ordered pair. So over 1 on our x-axis, and then up 2 on our y, we get this point, 1, 2. Then we would have -1, -8, -1, 1, 2, 3, 4, 5, 6, 7, 8. So we're off. That one doesn't fit on our grid. I don't know if the one on the paper is the exact same size, so check yours. Then we would have 312. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Somewhere up here, right? It's going to be off the grid. 2, 7. 1, 2, 3, 4, 5, 6, 7. And 0, -3. Okay. So there's the plotting of all of the points that we identified, realizing that some of them don't fit on the grid. And finally, part H. This is our visual representation. My question for you, what is the visual representation of all the solutions? So from part F, remember, we are recognizing that there's an infinite amount of solutions. So if we could visually represent that, all the infinite amount of solutions, what would that actually look like? Hopefully you're thinking it would be a line, okay? Because we could find some points in between every single one of these points that we already labeled or that we already plotted that would connect, whoops, here, let's use my line tool, that would connect and make a line. Okay, we would need arrows on both ends because it's going to continue on in both directions forever. So this line represents that the infinite amount of solutions to this problem. So not only are those points solutions, but everything in between them would be, and those aren't going to be pretty points necessarily. They're not going to be integers necessarily. They could be decimals, they could be fractions. And we could continue this on forever. We could make a humongous graph, and as big as we could make it, we would still be continuing it on and finding more and more points. Okay, example 2, the sum of two numbers is 14. What are the numbers? Okay, so first, to do this problem, part A, identify two variables to be used in this situation. Explain the meaning of each. Well, what we are trying to find are the numbers. There are 2 of them, so let's have 2 variables. And it doesn't matter what you pick. I'm going to pick x and y because I'm a little boring, but you could pick anything you want. Any 2 letters you want. X will just be the first number, and y equals the second number. Anytime you're asked to define a variable or explain the meaning of each variable, they want you to not only give the letters, but they also want you to say what they stand for. So something just like this is fine for an explanation. Part B, create an equation using these 2 variables to represent the situation. Well, it says the sum of the 2 numbers is 14. Sum, hopefully you know, means the operation of addition. So if we add these two numbers, we have to equal what? We have to equal 14. There's the equation. List at least 5 solutions in the equation you created in part B. Okay. Well, what two numbers could you add together and get 14? My first thought was 10 and 4. So 10, 4. You can add those together and you can get 14. You could add 7 and 7 and get 14. You could add 0 and 14. You could add 4 and 10. Okay, just like we had 10 and 4, we could switch the order of any of these. We could say 4 is our first number and 10 is our second number. Or we could say 10 is our first number and 4 is our second number. You could also do, let's do maybe 3 and 11. You could have picked different points, wouldn't have mattered, different numbers, wouldn't have mattered as long as you add them up and you get 14. Create a graph that represents the solution set to the equation. How can we do that? We can plot our points. So 10, 4. Ooh, I didn't do a, okay, that's all right. So we have X and we have Y. 10, 4. I'm going to change these. I'm going to make this count by ones here instead. Okay, so be careful because down here you're counting by ones now, and up here you're counting by twos. So 10, 4, I've got 10 here, and I've got 4 there. 7, 7, here's 7, and I'm going to be in between here. 0, 14, 4, 10, and 3, 11. Again, I'm in between there. Okay, so those are my points here, but those are only the 5 solutions that I happen to list here. How many solutions would there actually be to this? A whole lot more, right? Because not only could I come up with all the other whole numbers, but think about it. What if I wanted x to be 3.1? Could I find a y that when I add to it, I get 14? Sure. I could put a 0.9. 0.1 plus 0.9 would give me 1, and then I would need to add 10 more to that. So you could come up with all of the decimals in between all of the whole numbers, which means you have an infinite amount of solutions again. Draw your line in to represent that. Would I keep going in both directions? Yeah, because you could technically put negative numbers in here too, right? Couldn't I say that x is negative 3? Then what would y have to be to equal 14? It would have to be 17. So I could get negative numbers continuing on in both directions. Could you have, no, that's good. I'll leave it there. Okay, example 3. Mr. Sullivan had 14 songs in an oldies playlist composed of songs from the Beatles and Elvis. How many songs did he have by each in the playlist? Okay, and we aren't actually going to necessarily figure that out because you would need more information, but we can come up with possible answers. Part A, identify the variables. Part B, create the equation. C, list the solutions and then graph it. Okay, pause the video. You guys try it. Do all 4 parts here, A, B, C, and D. Stop there. Okay. Part A, you could have chosen any variables, but this time I went a little crazy. I didn't use X and Y. I used B and E. B for the number of songs by the Beatles, E for the number of songs by Elvis. Something I often see students do is they'll just write whatever their first variable is, and they'll just write, like, on this problem, they would have just written Beatles. Or they would have written S and songs. those are not specific enough. B for Beatles doesn't tell me what are you counting the number of bugs on the ground? I don't know what you're doing. S for a number of songs, well, songs by who? Which person? So you need to be very specific when you are identifying your variables and tell me exactly what it stands for. It's not just the Beatles and Elvis. That's not enough. It's not enough just to say it's the number of songs. You have to say which person's doing them or which group. So be very specific. Also, indicate whether it's number, whether it's a dollar amount, what are you actually talking about? So very specific as much as you can be when you identify your variables. Part B, pretty basic equation. We would just add them up. Okay, add the number of songs by the Beatles, add the number of the songs by Elvis, and you should get a total of 14 songs. Part C, you might have some of these same numbers, you might have chosen different ones. Could you have negatives in this list? I think no, it's not possible to have a negative number of songs. The smallest number you could have for either of them would be 0, and the greatest number you could have would be 14, okay? So you would not have any negative numbers in this list. And then putting your graph in, you should have plotted some points somewhere along this kind of stretch here. You might not have had the exact same ones if you didn't pick the exact same ones that I had, but you shouldn't have like anything super crazy. And also I did change my scale to 1 on the bottom. All right, finally, we said we wouldn't have negative, so we wouldn't continue our line down here into this negative region or over here in our negative y values, but let's think about some more. Would we have an infinite amount of solutions on this problem? And this is where question E part comes in. Compare your solution sets of examples 2 and 3. How are they alike and how are they different? Technically on this problem, you would only have integers as an answer. Integers being numbers like, and actually you could be more specific here, we only have whole numbers for our solutions, 1, 2, 3, 4, 5, 6, etc. We would not have decimals, we would not have fractions. You can't have a decimal of a song. Well, maybe if you were back in the day you downloaded it and it didn't download completely. But assuming that's not happening, you wouldn't have a decimal or a fraction of a song. So your solutions would only be whole numbers. So you might have other points on here, but they're all going to be whole number points. You're not going to have any that are decimals or fractions. So you would have all of these purple and red points, but you would never be able to get a point like this. You wouldn't have 2.5. You don't have 2.5 of a song. So technically, you would not draw the line in here. This is called discrete data. Discrete data is when we are only going to be working with either whole numbers or integers. So only integers, or more specifically in this case, it's whole numbers. So a better way to think of it, no decimals, no fractions for this problem, okay? That's what makes this discrete data. So what is actually discrete data? Discrete means it's only certain data points. Okay, it's not going to be all solutions. The opposite of discrete would be a problem like this one, where you actually have a full line, and that is called continuous data. Okay, easiest way to think of it, continuous data, you can continually, whoops, I'm not drawing a straight line, but continually keep drawing. You would never have to pick up your pen. Versus discrete, when you're doing a graph that's discrete, you have to pick up your pen between your solutions. Okay, this isn't something that's going to be tested right now, but I just wanted to talk about that for a second. I'm going to make it easy on you. I'm going to allow you to draw your lines in at this point and not have to figure out if things are discrete or continuous, but little preview of what you'll see in the future. All right. Okay, off you go. Finish your packet.